Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this is part 2 of a series of essays on classification and discrimination. It's all part of the course, Analytic Methods for Lawyers, but it may be of interest to a broader audience. In the prior essay, I showed how a classifier could generate different statistics, such as accuracy, false positive rate, true positive rate, for different groups, even if group membership did not have any causative role in whether a person succeeded or not. That's a bothersome fact. And we could perhaps create greater equality if we could just strengthen the performance of the classifier on the group with inferior statistics. That's a worthy task, but it's also often quite difficult. So in this essay, I want to explore how we can instead weaken the results of a strong classifier. Doing so can let us generate statistics for the group formerly treated better that are closer to those for the group formerly treated less well. I'll show that it can be done not only by degrading the algorithm itself, but by a combination of changes in the threshold and imposition of a random element. And for those worried about the costs of weakening a classifier or introduction of randomness, be patient. That's the topic of the next essay. Now, there are 3 basic ways you can change the statistics for a classifier. You can use them together or individually. One is threshold manipulation. Remember I showed you that ROC curve in 3 dimensions? That tells us there's a relationship between threshold, false positive rate, and true positive rate. And I can call those 2 latter things, by the way, the reality-dependent positive rates. And so if there's a change to the reality-dependent positive rates, there has to be a change to the overall positive rate as well, because it's just a weighted average of the 2. And if there's a relationship between threshold and reality-dependent positive rates, then there has to be a relationship to accuracy as well, because accuracy is also a weighted average of the false positive rate and true positive rate, just a different weighting. So by changing the threshold, we can definitely move about in performance space. Threshold manipulation standing alone, however, has its limits. It just really lets us move up and down the ROC curve. We certainly can't go up and to the left of it, because if we could, then the classifier would, by definition, have a higher ROC curve. And there's also no way of moving down and to the right either. The classifier does what it does, and if this is our only tool, all we can do is move along the threshold move along the ROC curve by changing the threshold. A second thing we could do would be to basically weaken the classifier. And you can do this in several ways. The first thing you could do would be to blur the data. Presumably, if the data reveals something, then adding enough noise to that data is likely to hurt the performance of the classifier. Similarly, although random withholding of some data can often help a classifier be more robust, as we saw in the discussion of random forests and dropout layers, that occasional deprivation is a lot different from never letting the classifier see relevant data. Imagine the example used in the prior essay. Supposing we'd prohibited the classifier from ever seeing income. Our classifier's performance would deteriorate because the only other variable, race, that it could see was constructed precisely so that it would have no effect after income was taken into account. So, alternatively, you could just weaken the classification algorithm. You could use fewer than optimal layers in a neural network, or different than optimal nodes in a layer, or just design the network architecture poorly. You could use fewer trees in a random forest, or lower the number of iterations used in gradient boosting. You could use an excessively shallow decision tree, and more. It's just not that hard to make a lousy classifier. The third method, and the one I want to focus on here, is stochastic methods. Let's start with random flipping of results. You can make this prediction dependent or classification dependent. You could say that in 20% of the cases where the classifier says negative, the classification is changed to positive. And in 40% of the cases where the classifier says positive, the classification is changed to negative. Alternatively, you could use stochastic thresholds for determining positivity. Perhaps 30% of the time, a probability of 40% is required to be classified as positive, and 70% of the time, a probability of 90% is required in order to be classified as positive. The classifier weakening method that we discussed can be emulated by either random flipping or stochastic thresholds. In other words, instead of doing this, which weakens the classifier, you can just take a good classifier, flip its results, or impose stochastic thresholds. And indeed, these latter methods can force movement in the performance space in ways that threshold manipulation cannot. Let's consider random flipping of results. Let's say we have a confusion matrix, and I hope you know that FPR stands for false positive rate, TPR stands for true positive rate, I stands for incidence, and I'm just going to assume that the sum of the elements in the confusion matrix is 1. So that's going to make things simple, and it doesn't change anything. So here's our original confusion matrix. These are the people who are truly negative, so we're going to multiply all of their stats by 1 minus I, the incidence. These are the people who are truly positive, so we're going to multiply all their stats by I, the incidence. And there are the false positive rate times 1 minus I here. These are the true negatives, so we're going to multiply the number of people who are negative by 1 minus the false positive rate. These are the people who are true positives, so we'll have the incidence times the true positive rate. And these are the people who are false negative, so we have the incidence times 1 minus the true positive rate. So here's a picture of our confusion matrix as we start off. But now, let's apply 2 transformations to the matrix. For those who are originally classified as negative, that's these people here in this column. Remember, our convention that I've been very consistent with is reality is on the rows, classification is in the columns. So these people who I've classified as negative, I'm going to change a fraction alpha of them to positive. That fraction has to be the same for this first row here as it does for the second row here, because by definition I don't know whether the person is in fact negative or positive. If I knew that, we wouldn't be here. And for those who are classified as positive, that's this column here, I'm going to change a fraction of them, omega, to negative. And again, it has to be the same omega here as there, because I can't tell whether this person is really negative or really positive. Again, if I knew that, we wouldn't be making classifiers. So here's a little bit of programming to do this, but at the end of the day, we're going to end up with the following expression as the new confusion matrix. And you can see that everything is just a function of the incidence, the flip rate alpha for the classified negatives, the flip rate omega for the classified positives, and our original false positive rate and true positive rate. Okay? So you can do the math out yourself, or you can trust me, but this is what our new confusion matrix looks like after we do the random flipping. Well, let's calculate what's the new false positive rate and true positive rate as a result of our flips. So the new false positive rate is this element, first row, second column, divided by the sum of the first row. That's this. Our new true positive rate is the second element, second column, that's this, divided by everyone who was positive. And so we can calculate that here. I'll tell it to simplify. And this stuff here is just to make it big and frame it, because this is the key result. So this is the new false positive rate as a function of the old false positive rate, plus alpha and omega, the flipping coefficients, flipping values. And this is the new true positive rate, which is a function of the old positive rate. And again, alpha, the negative flips, and omega, the positive flips. So if I start with some value of false positive rate, an initial false positive rate, and an initial true positive rate, by varying alpha and omega, I can sweep out a range of new false positive and new true positive rates. Let's look at what those are. Okay, and so what we see is that we start here, here's our original false positive rate and true positive rate, and with flipping, I can get anywhere in this diamond that I want. If I change the original true positive rate, I just move the diamond. If I change the false positive rate, I change the diamond, okay? But what I've done by permitting flipping is to get anywhere in the interior or boundary of this diamond here. And so that's going to enable me to weaken a classifier, right? If I move, for example, in this direction here, I'm getting both, or let's say, actually this direction here is worse. If I move in this direction here, towards the 45-degree line of a random classifier, I'm getting a higher false positive rate, that's bad, and a lower true positive rate, that's also bad. So we can definitely weaken the classifier this way. So we have a diamond, and instead of using parametric plot to sweep out the diamond, I can recognize that we really can define the diamond by 4 vertices. This is when there are no flips. This is when we're doing 100% flipping. Whatever we see, we say it's the opposite. Sometimes I do that at faculty meetings with colleagues I don't like. Let's write a little function to create the diamond. And we'll now take an ROC function. This is just parameterized not as of the threshold, but as of the false positive rate. So we're saying you give me a false positive rate, and I'll spit back the true positive rate. And so if we let FPR go from 0 to 1, we'll get both the false positive rate and the true positive rate, so we'll sweep out an ROC curve. And so now what I'm going to do is I'm going to sweep out an ROC curve, and then I'm going to make 19 diamonds that are drawn when the false positive rate ranges from 0.05 to 0.95, and I'll keep my 45-degree line showing the ROC of a random classifier. So you can see faintly all the little diamonds, and I can get anywhere that's shaded blue. So what this means is I can get anywhere within this football by changing the threshold, so I start here, and then making my diamond, okay? So what we've done is by letting me migrate along, again, just to repeat, letting me migrate on the ROC curve by changing the threshold, which in turn changes the false positive rate, which changes the true positive rate, and then flipping, I have complete freedom to navigate, basically, the interior of the ROC curve. I still can't get up here because this is a better classifier. That requires sort of a technological change, maybe better data, better algorithm, something. But what I now can do is I can now get inside the classifier. All right. So now what you might be thinking is, great, but why would I ever want to move to the interior of an ROC curve? Well, suppose you had 2 classifiers, one for each of 2 groups with non-identical ROC curves. We actually saw that in the first video, where the ROC curves for the majority were somewhat different slightly different from those of the minority. What this means is that if I want to do so, you can move the result, false positive rate, true positive rate, of the stronger classifier arbitrarily close to the result of the weaker classifier. And that would produce greater equality in the treatment of the 2 groups. It would be a cure for the discrimination created by the original classifier. Of course, that cure might have some costs, but we're going to hold off on costs until the next essay. This one's about movement. So let's take an example. Suppose we have a classifier for group 1. You actually saw, that's the ROC curve there, Roc 1. And now let's build a second ROC curve. And the only thing really different here is that that exponent is 2 rather than 5. Okay. So here's our second ROC curve. And what we're going to do is we're now going to find the optimal point. And for the moment, I want you to assume that the optimal point is where the true positive rate is most different from the false positive rate. Maybe I should use FPR here. Kind of like that. Let's do that. Right? So it turns out that that's where the false positive rate is about 0.331. And on the second ROC curve, okay, let's not use X, let's use FPR. It turns out that we maximize the difference between the true positive value and the false positive value when the false positive rate is 1/2. Okay, so now we're going to show that graphic. It's going to be very, very similar to this one, except now I'll have 2 ROC curves in it, one for group 1 and one for group 2. See, ROC1, ROC2, and we will have the optimal points that will be labeled. That's what this code here is doing. All right, let's do it. And there it is, a beautiful graphic. Here's the red for group 2, the blue for group 1, and what we can see is, of course, that the false positive rate is lower for group 1 than group 2, and the true positive rate is higher for group 1 than group 2, and so the group 2ers could be very unhappy about this. Okay, so what could we do? Supposing we want to change the true positive rate for group 1 to be equal to that of the true positive rate for group 2. So we need it to be right here, okay? If I move horizontally. So I've got to slide down the ROC curve. And the way to slide down the ROC curve is to set the threshold higher. That means that fewer people will be classified as positive, so we'll have fewer true positives and fewer false positives. So we can do the math here, and I can find out when is the true positive rate for group 1 at some value of FPR equal to the true positive rate for group 2 evaluated at 0.5, which was that optimal value that we found up here. All right? So we're going to use a little algebra, and it turns out that the false positive rate we need for group 1 is 0.242, and using the eyeball method, you can see that if I use 0.242 and I wiggle it enough, we get exactly where we want to be. All right, so let's draw a new diagram with the false positive rate for group 1 set to this value 0.242 and the true positive rate corresponding to that point on the ROC curve. So there we are. Okay, so now we've got equality in the true positive rate for group 1 and group 2, and we accomplish that by changing the threshold. But what if we want our false positive rate to be closer to the false positive rate for group 2? Well, we need to start moving along this line here. We're going to have to get into the interior of the ROC curve. But we already learned how to get into the interior of the ROC curve. We do some random flipping. So let's find the set of flips that preserve the true positive rate. And it turns out that so long as omega is equal to negative blah 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 with the true positive rate and alpha in here, then we're going to preserve the true positive rate. So I can take this expression, TPR preserving, plug in the true positive rate of 0.75 for our friends in group 2, and I should start to get a little more concrete information about the relationship between omega and alpha. And so what I need is for omega to be 1/3 of alpha. And if that's true, I get my preservation of the true positive rate. And so as long as I keep omega 1/3 of alpha, I'm going to start moving along that line. Okay, so we can see a little bit further what this is going to look like. This is the new false positive rate as a function of alpha, and we can find out for what value of alpha does our new false positive rate for group 1 equal 0.5, which is the false positive rate for group 2. And it turns out that alpha is 0.380803, and that means that omega has to be 1/3 of that, which is like 0.1267. And so that's the flip that we need to do. What we do in order to achieve complete equality between group 1 and group 2 is we up the threshold so that we drive the true positive rate and false positive rate down, and then we flip. We say 38% of those who are negative, I am now deeming you as positive, congratulations, and sorry 12.67% of you who we originally predicted positive, you have now been randomly selected to be deemed negative. Okay? Are there other ways of getting from our original point up here to here? Sure. We didn't have to change the threshold in this instance. We could simply have done different values of alpha and omega that would have moved us there. There are instances, however, where you are going to need to wiggle the threshold a bit in order to get to another point on the interior of the ROC curve, and that's why I showed you that complexity here. Instead of using random flipping, we can actually get the same result by use of stochastic thresholds. Here's the idea. We're going to subject a group to 2 different thresholds, and which threshold you get is randomly determined. So supposing 30% of group 1 is subjected to a high threshold, so that the false positive rate is 0.2, and the true positive rate is the value of the ROC curve at 0.2, which happens to be 0.67. 70% of the group, though, is subjected to a low threshold, such that the false positive rate is 0.6, and the true positive rate is the value of the ROC curve evaluated at 0.6, which happens to be 0.989. So what's the average false positive rate? The average false positive rate is just the weighted average of the false positive rates, with the weights being the fractions subjected to each threshold. And I guess I pre-computed this here before we had a little computer glitch. So it's 0.48. And the average true positive rate is just the weighted average of the true positive weights. So it's 30% times the value of the ROC curve evaluated at 0.2 plus 70% times the ROC curve evaluated at 0.6. And that turns out to be 0.894528. So what we can do is we can draw a line between the 2 thresholds, and every point on that line is obtainable depending on how much weight we give to each threshold. So here's our graphic. Here's our 2 threshold points. Here's when we have a high threshold, so the false positive rate is low. Here's when we have a low threshold, so the false positive rate is high, as is the true positive rate. And we're going to move 70% of the way along this line. So if you think about it, that means that by setting our 2 points, our 2 threshold values, and figuring out what weight we want to give to each threshold, we can move anywhere we want on the interior of the ROC curve. We can't move down here because there's no points that'll get us there, but we never want to be down here. This is worse than a random classifier. So we can certainly get to here using 2 random thresholds, and we can really get wherever we want. So let's actually see that. Let's write a little function that makes one of those connector lines based on the false positive rates that we give them and the ROC function. And now let's make 20 lines. All right, and there we are. And yes, of course, I haven't covered every single point, but I hope you can see that I certainly could if I wanted to. So instead of using random flipping, we can subject people to random thresholds, and functionally it's the same thing, although they might not perceive it to be the same. So I want to give you a little sneak preview of what's coming in the next video. And the idea is to finally look at the costs of all this weakening of classifiers. Let's take an example. Supposing, regardless of group membership, a false positive has a cost of 2 and a false negative has a cost of 1. Suppose further that in group 1, 80% of the group is actually positive, and in group 2, 60% of the group is actually positive. Finally, let's suppose that the fraction of the population in group 2 is some fraction m. And let's let FPR1, TPR1 be the statistics of our classifier on group 1, and FPR2, TPR2 be the statistics on our classifier for group 2. So let's start writing the total inaccuracy cost of our system. All right, so it's a weighted average. Here are the two weights reflecting how many people are in each group. 1 minus m for the majority and m for the minority. Well, what are the inaccuracy costs for the majority? Well, 20% of them are negative, and so for them, we're going to take their false positive rate and multiply it by the cost of a false positive. 80% of them are positive, so we're going to multiply that by the number of them that are false negatives. False negative rate is 1 minus the true positive rate, multiplied by the cost of being a false negative. And we're going to do the same calculation here for the minority. 40% of them are negative, so their costs are the false positive rate for them, multiplied by the cost of being false positive. And 60% of them are positive, so we're going to multiply the false negative rate for them by the cost of being a false negative. And when we add all of that up, we get a little expression for the inaccuracy costs. Okay? So now, supposing we value equality, so that we also say there's a cost equal to 1/10 of the Euclidean distance between the false positive rate, true positive rate of group 1 and the false positive rate, true positive rate of group 2. And Euclidean distance is just the square root of the sum of the square differences of the coordinates. It's just the Pythagorean theorem with a fancier name. I guess Euclid usurped it or something. So the idea is that if the the 2 points are right on top of each other, then there's no inequality cost. On the other hand, if the 2 points are very far from each other, then there's a high inequality cost. So here's our little formula for the inequality cost. It's the Euclidean distance, and just for the heck of it, I'm going to divide that by 10. Obviously, if I divided it by 1,000, then perhaps the inequality wouldn't matter that much. On the other hand, if I didn't divide it at all, then inequality might matter a lot. All right, so now let's bring out our friend and minimize, and let's take the sum of, let's make sure the inequality costs are in our kernel. There they are. The sum of the inaccuracy costs and the inequality costs, I'll plug in 0.2 for m, and here are our constraints. The constraint is that the true positive rate that we're getting for can't be bigger than the ROC value evaluated at the false positive rate. That would mean that we're making the classifier too strong. We're going to bind the false positive rate to be between 0 and 1. For the second classifier, we have again this ROC constraint that the true positive rate for group 2 can't be bigger than the ROC curve evaluated at the corresponding false positive rate. And we have our constraint that the false positive rate has to lie between 0 and 1. And I'm going to tell our little guy, please find me the values of FPR1, TPR1, FPR2, and TPR2 that minimize the sum of the costs subject to the constraints. Ready? Here we go. And it did it. So you'll notice that the two values are not equal to each other, but they might be closer than they were if, for example, I divide, in fact, let's just do it. Let's divide the inequality costs, not dividing it by 0, let's multiply it by 0. And now let's figure out what the optimal is. And now the optimal, you'll see there's a greater difference between the two because I haven't valued inequality at all. All right, so that's a little bit of a sneak preview of coming attractions. For now, what we've learned is how to weaken a classifier, primarily by a combination of adjusting the threshold that we're going to use to classify something as positive, and then by randomly flipping fractions of negative and positive predictions, or conceivably the random threshold measure. And this flipping will enable us to get a classifier to obtain false positive and true positive values at any point at or below the original ROC curve, and that ability to move, that freedom, will permit us to achieve any goals we have for equalization of the results of the classifier among different groups. Thanks.